Conclusion from this little investigation is that I have to go individually to allow you. So now you can record that.
Yes, thank you. But
Are you
I'm not
already recording the lecture?
Yeah, you can record what is happening now, the whole session, the whole discussion. Okay, here you go. I see you recording it. Okay? Anybody else wants to record or? No, no volunteers. Okay, let's go back to the class, okay? You guys listening, I hope, right?
Yes, we are.
Okay,
Yes.
Listening, sir.
okay, so we have one student is recording, Alhiba. Am I pronouncing it properly, Alhiba?
Yes.
Okay, she is recording it. Now you have to pay her $5 and you get your own recording. Okay.
Yes, I think.
All right. Okay, I'll go back to the business. Okay, share screen. And here we go. And I go full screen, okay?
I have a question about this slide, Professor.
This one, this particular one, yes.
Yes. What does tau represent again?
Okay, I don't know how you guys doing in statics. In statics, you have sigma and tau. Don't you have the normal force, the pulling force, or sigma, which is like pressure, and then you have tau, which is the shear, which is force, but sideways. Are we on the same page or?
Yes, yes, we are. And then you said the mu represents the viscosity?
Mu is a property. Okay, so this whole discussion is about properties, so density, and I'm going to list more properties just so we know what's going on. However, this particular one is very important. So that's why I'm staying on it a little bit more, because it has those three elements which I mentioned down here. And so if you understand this picture, that the upper surface is moving, the lower surface is stationary. And then because of that, we're going to have a velocity profile that appears like in that picture. Okay, that's what I'm trying to sell you. And then if you agree to that, turns out that in order to create this velocity profile, we need to pull the upper surface. But the fluid has some viscosity, which you can call friction. And therefore, we need to apply force. So the question is, how much is the force? So if I would like to use it that way, I would say, instead of tau here, I would say the force divided by the area of the plate is going to be equal to mu du dz. That's Newton's formula, okay? And then I think the next slide is an example. The next slide is going to be an example. And then, so number one, fluid must be in motion. And then the no-slip boundary condition, which I'm trying to talk about it more and more and more, which is kind of strange initially. And then Newton law of friction is these formulas. This is that one. Again, example is coming. And this is for this particular case because the shear is just a straight line. I mean, the velocity profile is a straight line. So du dz is some sort of a constant, which is u over h, if you just take the derivative of the equation. Now, just an anecdote. Oh, by the way, here's some materials with density and then viscosity to them. So air is very low viscosity, 10 minus 5. And then you look at motor oil, which is kind of 0.3. So that would be SAE30. SAE20 would be maybe 0.2 and so forth. So it's very close to that. Mercury has very high viscosity and all that. And glycerin is high as well. So these are properties. You don't have to carry a notebook. This is jump automatic. I don't know why it is. Okay, I got it back. Okay, and that's it. Now, just a little story. People looking at fish, and then they say some of the fish has so much power and going so fast, and the only explanation is they have less friction than meets the eye. So then people say, well, but then there's a no-slip boundary condition. The fluid has to stop. So the fish experts tell you, oh no, the fish actually has some mucus or something they release from the surface, and therefore the particles are not actually stopping at the surface, they kind of sliding through, therefore the friction is less. I don't know if the story is correct, but again, makes a good one. Okay, let's do an example. Now on the right hand side, you see that viscosity is actually depends on temperature. So, and those with the car guys or car people know that the higher the temperature, viscosity is lower. That's why they say 1020 or 1040 motor oil, the same one. Air, by the way, viscosity goes slightly the other way, and hydrogen or gases, but liquids are usually viscosity goes down. Anyway, usually students ask me if you have to remember all those. No, when we're gonna have homework or exams, we'll give you the property. I don't want you to remember all kind of strange numbers. So here is an example. Now we're looking at this picture. Okay, let me do it carefully. This is the picture I'm looking at here. So the upper plate is moving, the lower plate is stationary, and there is motor oil SA30 in there. The upper plate moves at 3 meters per second, and viscosity is 0.29, as we've seen. And then the question is, what is the shear force per 1 meter square of the upper surface? Then later I'm going to ask for 2. So imagine the upper surface is infinite, but we're trying to look at a segment of 1 meter by 1 meter. So the shear force, what is the shear force? Is the force which was F per 1 meter square. It's going to be mu, which is the 0.29, the viscosity. Upper surface velocity is 3 meters per second, divided by the spacing, which is 2 centimeters, so it's 0.2. And I forgot to mention that the spacing between the two plates is 2 centimeters. Therefore, you use simple algebra, it turns out 43 kilograms per meter squared. And that's 43 Newton per meter. So units are exactly like pressure. So now if you have 2 meter square plate, they just simply multiply by 2. Okay, very, very simple example. Okay, so we are in a mode where I'm surveying all kind of properties. So we're really not going to discuss too much temperature changes, but still, so specific heat. So you have 1 liter of water or 1 kilogram of water, and you want to heat it by 1 degree centigrade. It's going to take you 1 kilocalorie. Well, it's a kilogram, it's 1 kilocalorie. That's, by the way, the definition. So CP is going to be 1 kilocalorie per kilogram, which is at constant, so that's specific heat at constant pressure. You can do the same experiment, constant volume, assuming things do not expand. This is particularly important for gases, not for liquids, which do not expand. And this is a slightly different number, very similar, but slightly different. Again, for gases, there is a gamma, and anybody who is an expert on thermodynamics know all these things. And then the gamma is simply the ratio between Cp and Cv, and it's typically larger than 1. For air, it's going to be 1.4. Okay, so that's it. I just mentioned that so you know that. Then there is a heat transfer coefficient. Again, from high school, I'm sure you did that, unless you went to the beach instead of high school. And here's the scenario. I still have all the students with me. I have 133 of you.
Yes, we
You're good. Okay.
Yeah,
Occasionally we make a sound, so I don't think I'm talking to myself. I mean, so far so good. So you understand what I'm saying? Or?
yeah, seems clear to me, Professor.
Makes sense. Okay. So now, okay, let's talk about heat transfer coefficient. So there's a wall. That's the wall in your house. Okay. And outside temperature is T2 is high. Inside temperature is cooler. It's T1. Then we put a coordinate system X, which goes from inside to the outside, like you see here, the coordinate system, okay? Coordinate system. So the question, and then of course the wall thickness is D. And then the wall will have a property which is called the heat transfer coefficient, and it's a K, this K in the equation, okay? this K in the equation. So now, how much heat I'm losing through the wall? And then this type of calculation is good for people who design air conditioning. So A is going to be the area on the surface, okay? And it is going to be this K, which is the property, the heat transfer coefficient, and then the change of the temperature along this D. Okay, so we assume again that the temperature change is linear, and if the K is constant, it is linear. So if I translate that equation, which is called the Fourier equation, very similar to what we did before, then it looks like that. Minus K, A is the area here. The gradient is T2 minus T1 divided by D, by the thickness of the wall. Why is the minus sign? Because the heat transfer is always from the high temperature to the low temperature, okay? So if the gradient, the temperature is increasing towards the X direction, the plus X, actually the heat transfer will be into the opposite direction. Is it good? If no objection, I continue. Okay, again, I presume seen that. And in this particular course, we're not going to focus on temperature changes or variation. But again, we're talking properties, I have to mention that. Okay, here's another one. Surface tension, we're gonna call it sigma. And some of the stories goes like that, that each particle is pulled like here in the middle, pulled to 4 directions. Once it's on the surface, the poor particle has nobody pulling him up, so they pull to the side. And in order to keep that place kind of horizontal, somehow on the side, the force has to go either up, but they has to support somehow this surface. How do we measure that? There's a simple measurement. We can have some kind of a U-shaped metal frame, and then maybe something flexible. And let's say we have a soap film on that, and we try to pull with the force F. The moment the thing falls apart, we say that's the maximum force. And we can say a formula that the force is equal sigma over the length. So we're talking about a surface tension force, which is defined by sigma. So sigma is a property of the material, and it has a list of quantities. So here's that next one. Okay, here's a table. I repeated the same table, but now I add the sigma. So some of the properties are very small numbers. And anyway, in the future, I'm going to give it to you in particular problem. I don't need you to start looking into Google and figure out how much is the surface tension. Again, the significance of that was basically in the past when they've been using tiny tubes to measure pressure. They call them manometers. And then because of the surface pressure, there was what's called a meniscus, where the fluid turned. We'll get the next problem is that. So let me stop with that for a moment and continue with this thing. So if there's a surface tension, then let's look at a bubble or a droplet. Why would a droplet be circular or a bubble would be circular? And why it holds together? So let's look at this picture. And by the way, for this type of model, those two cases are identical. Either it's a full droplet or it's a bubble, okay? So we're looking at the surface, we're kind of cutting the bubble into 2 halves, okay? So what is pulling it together? The surface tension between the particles on the peripheral area. So it's gonna be the area, the length of the circle is 2 pi r and times sigma. So that's the force F sigma that is pulling the bubble together, okay? What is trying to push the bubble to the sides is the pressure. So the pressure, which is pressure difference, is acting on the whole area, which is pi r squared. So these two forces should be equal. So we put them equal, and then we find out that the delta P must be equal to 2 sigma over the radius. Okay, very simple. Then we have here an example, just a very quick example. Calculate the pressure of 10 centimeter diameter. 10 centimeter is something 4 inches for those that don't know what a centimeter is, and a water soap bubble. And here it is. They say that for a water soap bubble, sigma is this number, 2.5. It's a very small number. So how much is delta P? It's going to be 2 times sigma over R, which is, here it's, I'll use capital R, doesn't matter. You plug in the numbers and it's going to be 1 Newton per meter square. So it's a very, very tiny pressure difference. Okay? That's an example. Again, all these examples are going to be posted on Blackboard eventually. Very simple. And this is, let me go back. It is not doing it. Oh, now it is doing it. Here we go. So surface tension, look at that. It's a force acting on the line. Sigma represents force per unit length, okay? Then here we did an example just for a bubble. Very simple, so how it works. Here are some of the sigmas for some units, which is, I'm repeating the same table, but now we're adding the sigmas. And now let's talk about the capillary effect. I tried to mention that people have been measuring pressure with those little tubes. So here's the little tube. Here's the little tube. And turns out that on the side, there is an angle theta, which is called wetting angle or surface force angle. Let's call it wetting angles. So if I want to translate this picture to you washing your car, and then the car is really kind of old paint and not very good, then your wetting angle is going to be less and the car is going to stay wet. If you did a good wax on the car, it's really smooth, everything wonderful, then the angle is going to be larger. So the droplets will stay like droplets on the car. So we call those non-wetted surfaces. So in this picture, the wetting angle is going to be less than 90. So it is going to pull up. And it's going to be larger than 90, like in, I put here the mercury, glass mercury interface, then the meniscus is going to point down and actually the fluid will go below the fluid around it. Is the story make sense? Somebody say yes or no?
Yes.
Yeah, it makes sense.
Okay. All right, so that's the story. So this is called, so now we can do the same example. Let's pick up a case when the wetting, the fluid is wetting and it's like, I don't know, coffee or something, it's wetting. So the angle is less than 90, therefore the fluid will climb up on the sides of that little tube. Let's say this is some kind of a glass tube. So how much is the force pulling up the liquid? It's going to be equal to the circle, the peripheral circle, which is 2 pi r, I'm putting it here. And then it's not full 2 pi r, but it's cosine theta, okay, because it's not acting straight up. And then times sigma. So, okay, so very simple. That's the force pulling it up. But this thing is in equilibrium. So what is the weight of the fluid that's being pulled up, which is the base, which is pi r square area, times the height, h, which is the height of the fluid, and then rho g. So this rho gv, that's basically what it is. So it is the weight of the fluid. Okay, so these two are equal to each other. And then you solve for h, for the height, which is going to be 2 sigma cosine theta rho g r. R is the radius of the inner radius of the tube. Okay, so again, very, very simple. Now, if you go through the numbers, turns out those things are very, very minor, and I have an example. But again, anybody seen, when they measured blood pressure in the old days, they used to have mercury. And the mercury had a meniscus which is pointing down, which is the 130 degrees. So that will introduce a small error in the measurement. Or if you measure speed, like with a water column, then also the meniscus or this thing will have an error. I'm not sure if you younger, much younger than, so you have not, everything is electronic nowadays. So you don't know what I'm talking about, which is not good, by the way, not good. Okay, let's do an example on the capillary effect. And I would like to use this formula. Let me go see if it works well. I want to use this formula in the bottom. H equal to sigma cosine theta. That's it, that's one. So let's do water. Turns out with water glass, the angle is actually zero. Then we're looking at the table, okay, and the quantity of sigma is 0.073 for that. And okay, so for water, and the tube is actually 1 millimeter diameter. So it's a tiny tube, very tiny tube. Some people say that that's how the trees suck the water from the earth, from the ground. So, okay, so what will be is 2 times sigma cosine 0, which is 1. Density of water is 1000 G. And then the radius, that means, what did I say? The radius, okay, I was afraid I said the diameter. Here's the radius is 0.1, so the diameter is actually 2 millimeters. And that's going to be 1.5 centimeter. 1.5 centimeter, like that, a little bit, tiny bit. It's a 3/4 inch. Okay, how about that? Okay, so let's do the same example. See, I'll have a phone next to that, okay. All right, I'm back with you. So now let's do the same thing. But now we push that little tube into mercury. Okay, so we mentioned the mercury, the angle is 130. Density is huge, it's 13.6 times heavier than water. And also the sigma is high, it's 0.48. However, because it's heavy, therefore we divided by the weight, and we ended up with a smaller number, but now it's negative. You see, the cosine 130 gives it a negative value, and it is actually going to sink below the level of the liquid in the container. Okay? So that's the example. Any question, make simple, or we just invented a simple formula. Okay, who likes mosquitoes? Okay, so here's a mosquito guy. He's walking on the water, and you're wondering why. He's not even religious. So question is, how can he walk on the water? And the answer is quite simple. Let's see. Sigma is 0.073 in the water. And then if we know the weight of the mosquito, which is 10 minus 4 Newton, it's a tiny creature. And then we assume that here is his leg. It's like a circular, and it's pulling on 2 sides with the force of sigma. Okay. Then the weight, okay, which is actually Newton, divided by the length. I put here S for some reason. The length, and which is 0.73. No, sorry, for sigma. Oh. Okay, apologies, that's supposed to be sigma. And I think it's, the symbol changed actually to regular, so anyway, but that's supposed to be sigma, and it's 0.73, that's the sigma here, and it's 1.36 millimeters. Now, the force is acting on both sides, therefore, it's actually a bit less than 1 millimeter length. So, which means that the mosquito can easily walk on the water. Okay, so that's this one. All right, let me go to another one. Did I change the full view? Okay, or what
Yes.
you see there? There was a change in the.
There was change in view, yes.
Okay, I wasn't sure. Okay, I'll go back here. The problem is if I do that, then I have your little pictures on front of that. Okay, I'll move it aside a little bit. Don't want to do it. Okay, so we finished with surface tension, very, very simple. I'm not going to work with that too much. It's not super important, but I just mentioned. Modulus of elasticity. Again, you took materials and statics, and you must have been exposed to that. So what is modulus of elasticity, or what is the force to compress something? So here's the picture. I put a piston, I put a gas in it, and then I'm trying to compress it. So look at this formula. So if I change the volume dV by the V, so that's the percentage of changing the volume, it's going to result in a pressure. And then for each material, the modulus of elasticity is this E. So that kind of measures how much force I need to compress something, okay? So that's the definition. Or if I take that definition, just work it around and just solve for E, then it's dP over dV dV. And if you look at that equation, then volume, so nothing, so the units of E must be the same as the pressure, okay? I'm sure you know that one, so it's nothing new. Now, the change in density and the change in the volume is the same. Okay, this is just simple definition. Therefore, instead of that equation or that equation here, I can just write it instead of volume, replacing it with d rho, d rho. So now I can, too many derivatives, so I can look at that and just take this portion, say dP d rho, and then I end up with E equal RT, okay? dP d rho equal RT, okay? So for an ideal gas, dP d rho, because it's P over rho equal RT, then it's going to be equal RT for an ideal gas. And therefore, E for the ideal gas is going to be rho times RT, okay? That's it. And then units, again, as I mentioned, it's going to be the same thing as pressure. Well, very simple. So just to make sure that this is another property of, this is also property of a fluid. Let's have an example and see how much is that. Okay, you know what, before the example, let me just make another note. In thermodynamics, actually the elementary thermodynamics, you collect the velocity of the particles with the velocity of a perturbation, a pressure perturbation, which is the speed of sound. And it turns out that the square of the velocity is dP d rho. But we already discussed dP d rho, and it's equal to E over rho. So we conclude that for generic material, it is E over rho. So now we have a formula to tell how much is the speed of sound in metal, in liquid, in all kind of other things. When we talk about the gases, it's more complicated, but we can take an ideal gas formula. Now, there is another assumption in the case of ideal gas, is that the compression of the gas due to the sound is actually isentropic, which means there are no losses. If there are no losses, again, thermodynamics, if anybody is, you must have taken thermodynamics, so you love that. You show that dP d rho is gamma RT, therefore the speed of sound is gamma RT.
Well, I'm taking it concurrently. I don't know if anyone else is taking it concurrently right now.
I strongly suggest remember these formulas. We're not going to deal with them too much, but it's a good thing to remember. Okay, for other cases. Okay, so I'll have an example in a minute. But let me finish with the compressibility. So I just want to show how uncompressible water is. So let's have water, seawater. So here I have, it's a little bit higher than regular water or something, 2.34, 10 to the 9. Okay, so that's the modulus of elasticity of water. And then let's think that we're going to a depth of 1 kilometer, which is 1,000 meters. So you take 1 0 out, this is going to be 100 atmospheres depth. Anybody understand what I just said? Anybody diving?
Can you explain it again?
Yeah, that's what I'm saying. Anybody's diving here?
No. Yes.
No, nobody's diving.
Not me.
You're just slipping. Okay, fine. So if you have a pool and it's 10 meters below, then the pressure is rho GV. If you do the algebra, after 10-meter depth, the pressure is going to be 1 more atmosphere than outside. Your ears are going to feel that. If you start diving more than 20 meters, there's going to be 2 atmospheres. Then it's going to be pretty painful. Now, remember when you're driving on the highway, you just go down and up a little bit and you already feel it in your ears. So if you go 10 meters down, 1 atmosphere, you're definitely going to feel that as a very high pressure. Now, we're going down 1 kilometer, huge distance, okay? 1 kilometer is almost 1 mile. Yeah, 1 mile is 1.609 kilometers for those that don't know it. So we go that deep, and I want to go dV equal dPE, which is the first formula I gave you. That's the same formula up there. I just plug in the numbers. So dP is going to be rho GH, density of the water, G, and the depth. So that's the pressure difference, which is about 100 atmospheres, roughly. Okay, and then divide by the modulus of elasticity for water, and big numbers, less than 0.5%. Okay, so it's almost no compression of the water, even if you go very, very deep. Okay, so that just to, again, we're not going to use many of those properties, but still we are introducing properties. And occasionally, you'll have to consider those. Not in this particular course. We're doing just elementary stuff. Anyway, so we are here, and let's do an example on the speed of sound. So I gave you the 2 formulas. One is for air, and one is for water. So I think in the homework, I'm not sure if I'm going to give it this time, but I usually have something that if you put your head in the water, or you're outside of the water, and then you see some noise coming from somewhere, firecracker or something. Where are you going to hear it faster, inside the water or outside the water? So let's see the speed of sound. Speed of sound in air is gamma RT. So 1.4, that's the gamma, that's the ratio of the CP over CV. We already mentioned R, which is the universal R divided by 29, which is the molecular weight of air. Let's assume standard temperature. 300 is like 27 degrees C, or 20 or whatever. It's close to room temperature. 300 to 47 meters per second. Okay, that's the velocity. Speed of sound in water. A modulus of elasticity, like I had it before, that's seawater. Density is close to 1,000. It's like almost 4 or 5 times more, much faster in the water, okay? So, so you have a way of measuring speed of sound. And another one is cavitation. And, let me go here. All right, so vapor pressure. So in centigrade, you know, in the, how to call that, the SI unit, it's quite simple because there is a vapor pressure inside the liquid. What it means, so when you go to a freezing temperature, when the change of it changes the shape from liquid to solid, then we claim that the pressure is 0. So for water, when it freezes to ice, it's going to be 0 degrees Celsius. And as we heat it up, the internal vapor pressure increases. And it increases until at 1 atmosphere, it is equal to 1 atmosphere. Therefore, we get boiling. So this is the pressure inside, it's boiling. So then you get the bubbles. So again, we're not going to speak about temperature changes, but let's just see why it is so important. So I want to cool your engine, your car, with water. And I would love to have temperatures higher. I don't want it to boil at 100 degrees. So what I can do is, one option is to change it. Say I want to go further up, I have to change the pressure. So the pressure inside the system, if it's going to be, say, 2 atmospheres, then I can go up to a higher temperature where I can actually continue. It's probably 120 degrees. Okay. So in the cap of your radiator, there's a number, and we chose what pressure the system was designed for, and therefore you can go to a higher temperature. So it's not going to boil at 100 degrees C. That's one of the tricks. Another trick that they do in a car, they put some antifreeze in there, which is not only antifreeze, it's also changing a little bit the boiling temperature. So this is one thing to remember. The other thing to remember is that in the fluid, when something is moving, and I tried to mention about Mr. Bernoulli, that he claimed that the faster the flow is, the lower the pressure. So now if I have this propeller and it spins very fast, then probably the fastest speed is going to be around the tip. And then the fluid still has to go around the tip, so the local velocity is even faster. So the pressure drops, but the vapor pressure is constant. So at that particular point, the vapor pressure becomes higher than the pressure in the fluid. Therefore, we get bubbles. And that's a very nice trick to visualize fluid properties or flow in that case. All right, I think that kind of, where am I now? That kind of summarizes, just let me see. I don't think there's anything else here. Professor? Yes, sir.
Can you repeat what you just said about the bubbles?
The story about the bubbles, okay. So in a liquid, it's actually, you can say it everything. There's equilibrium between different things. So there's equilibrium between the liquid state and then the gas state, okay? So, however, if the pressure in the fluid is higher, then the gas state cannot expand. You cannot form bubbles, for example, in the water. So, one more time. So for example, cooking, if you cook with the pressure cooker, you don't get boiling. You can increase the temperature without boiling the water. Why? Because you're increasing the pressure. So the vapor pressure increases, but the pressure in the fluid is larger, so you cannot form the bubbles. So the story goes that this can happen at any pressure. So you go up on the Himalaya mountain, you're going to boil the water, not at 100 degrees. It's probably going to boil at much lesser degrees because the pressure is lower, okay? So in this case of the propeller, again, we're going to learn about the Bernoulli equation, which states that velocity higher, pressure is lower. So if you believe me, at the tip of this propeller, okay, let me do that. At the tip of this propeller, the fluid velocity is much higher than stay in any other place. Therefore, if here the pressure is 1 atmosphere, here it could be the pressure maybe 0.6 atmosphere. So if the temperature, let's say 0.6 atmosphere, if the temperature is going to be 86 degrees or 82 degrees Celsius, then you're going to form bubbles in there, okay? Or in this particular diagram, if I look at 40 degrees C, then it has to be pretty low. So the pressure has to really drop in order to create cavitation, which is possible. So if this propeller spins very fast, then you're going to create bubbles. Are we explaining that property somehow reasonably? Who asked the question? Am I answering your question?
Yes, I just didn't hear you the first time.
Okay, all right. No, so at this point, you know, we conclude the discussion about properties. I must say the very important one is the viscosity. That's the most important one. Pay attention to that one. I showed some other things for general knowledge. Okay, so that's it. And I would like to start an introduction for the next chapter, which is going to be next week. So let's see here, we all finished. Okay, let me see that one. Yes, all done. All right, I stop share. So I'm back here on the, now, as I said, that we're going to follow pretty much the book, but not everything will be included. And sometimes there are more things over there. Sometimes there is more math for future. So then I also mentioned that I'm not going to hide the truth. I'm going to jump into the equation up front. It may be scary a little bit, but I try to make it as entertaining as possible, okay? And I know you're gonna ask me, do I need to remember that? You can ask and I try to answer, but probably by the end of next week, I can give you a much better answer of how much I want you to remember, okay? So we're gonna dive to the equation, and one more time, the reason for that is because that is gonna give us a logical way to continue and connect all the different examples to actually one case. And I think it's very, very important. Okay, so let me find the file where it is. So I just prepared some very preliminary thing. It is not in, it is in PDF right now. So, okay, here we go. Bless you.
Oh, thank you. I'm so sorry. I thought I was muted.
Okay, this is, I think this is that one. Yeah, I'm not sure how much can you see. You see how far can you see?
We can see maybe the little bit of the top of the diagram under 2.3.
Okay, so you see exactly what I see. I just want to make sure that you don't see.
Yes.
That. Okay, so I started pulling out some stuff from chapter 2, which is the fluid dynamic equations. And then first question is, which equations? So you probably will jump automatically say, oh, we would like to go at the momentum. Probably the energy. But then there's also conservation of mass. Now, again, some universities will have a course, which is a single course. It's kind of a math-oriented course, and they call it transport phenomena. And the transport phenomena is kind of generalizing all these equations. So then transfer of mass, transfer of momentum, transfer of green color, yellow color, of viruses from people to people, of energy, they all fit into the same equation. And we're going to discuss only these two, and I try to do them in a very similar way. So I'm not going to make your life too complicated, but I try to make it kind of simple, and we're going to focus on conservation of mass, or, well, that's probably the better name for that, and conservation of momentum. There's conservation of energy, which sometimes you can say it's dmq to the square. Remember, q is velocity. I mentioned that before, but I say it again. M is mass, q is the velocity vector, which is u, v, and w. And now it's going to be q squared for something which is moving. Again, in thermodynamics, particularly ME guys, you say that Q that you supply to a system, the heat, minus the work, is going to be equal to delta U, which is the internal energy taken by the system or by the fluid or whatever. Again, this is an important equation, but we're not going to work with the energy equation. You use that only when there is heat variation. If there's heat variation, then we have to go back and use the heat transfer, and then we have to use the K, and it's going to be becoming messy. So, and I don't think for undergraduates anybody does that. Okay, so at this point, I kind of convince you that, well, we're going to have two equations: conservation of mass and conservation of momentum, and they're going to be very, very similar. In this case, we have to figure out what are the forces. Then we have to make some decisions of how. And this is more a historical remark about Mr. Lagrange and Mr. Euler. Euler, remember, he developed some of the formulas, and he's very famous in mathematics and all that. So one of the questions, and actually these two pictures help explaining what's going on. Let me just bring it up. Okay, almost. These two pictures, this one and this one. I have here two stories. So there's Lagrange. Mr. Lagrange is the papa of dynamics. So he really wanted to look at the case where you take a chunk of material and try to follow it and then apply the equations of motion, which looks very logical at the beginning. Euler tried to propose some kind of a picture of perhaps streamlines or fluid lines, which is explained in the book, by the way, and which is kind of showing that picture. But if you pick up the coordinate system on the object which is moving, here I put an airfoil, I think in the book I have a fish, then you can probably draw some line and this picture may appear as a constant, okay, if you do it right. So then the next question is choice of coordinate system. So here's the situation. If I choose a coordinate system which is staying on the ground, okay, and then the airfoil moves, this is where the airfoil was, and this is where the airfoil is now. And I try to use the Lagrangian approach, and I'm looking at a particle. So this fluid particle did some kind of a loop like that. So now I have to write down the equation of motion with time and figure out what this chunk of fluid did. Are you guys still with me or ran away?
Still here.
You're still there. You understand
Here.
what I'm saying? Okay. So this would be a very complicated approach to solve the problem. The other problem is, as I mentioned, is the Eulerian approach, where we try to fix the frame of reference to the object, and then the fluid moves relative to the object. I can show that like a wind tunnel testing, when we sit and the model is there and then the wind is blowing. And then the picture we're going to see that is kind of this one, okay? So then we have to do one more little thing. So this is probably the best option, is to pick a coordinate system, which is going to be attached to the object that we would like to study the flow around it. Okay, so that's the easy decision, which we're following the Mr. Euler suggestion. But now, how are we going to write those equations? So turns out that we probably would like to define some kind of a control volumes. And I'm going to mention that many times. So we're going to look at the control volume and try to see the changes. Now again, I don't think you've been exposed to that type of story, and we'll see what happens. Now, why this is important? So one option is to try to figure out exactly what's going on in here. Where is the velocity? What is the pressure in every point? That would be called a differential approach, okay? Because I want to know the information everywhere. We can, since you have a control volume, I can look at the complete volume itself, and see what's going in, what's coming out, and if maybe there is no velocity up, no down, I can see just the total effect and perhaps figure out forces due to the integral approach. One more time, Daddy gives you $1,000 per month, and then you want to figure out your budget. So one approach is beginning of the month, I have $1,000, end of the month, nothing. Well, I spent $100,000. Or you can go inside the month and, oh, Monday I bought this, Sunday I went to the movies, then I filled the gas. So you can itemize each of these things and see what's happening. And of course, the differential will require much more effort. But at the end of the day, it should end up with the same result, which is you didn't save a penny. Okay, so, or you end up negative. So that's, and again, the money issue is very similar to what we're going to do here. So we're going to present both the integral approach and both the differential approach, and they're going to get the same result, but the math for the differential is going to be far more complicated. Now, so I go back here and I said, okay, this one I didn't explain, I'll explain, but here there is a force. So the force is acting on the fluid. So what are the forces? We did mention something, we mentioned shear and we mentioned pressure. So probably these are the forces that are going to be in. So what are the forces? So that's another discussion. So they're going to be body forces, so delta F, which is related to the volume. So I take one Coca-Cola bottle full of water and trying to figure out what is the force due to that. Now, if I'm going to hold it and the gravity, which is F represent body force, gravity is going to be G, 9.8. Coca-Cola bottle V is 2 liters, rho is 1,000. So, okay. So 2 liters is going to be 2 kilogram force, by the way. And so that's the delta F. That's going to be a force. So 2 kilogram force, which is 2 times 9.8, so 18.6 Newton. Anybody understood what I just said?
Yeah.
Yeah, okay. So this is body force. Or if I have a magnetic force, all these forces, both gravity, magnet, these are called body forces. They act on the volume and on the mass of the material. Okay, that's the point. Now, there are other forces which are surface forces. So the surface forces are shear, or pressure, very much like in mechanics. Okay, same thing. So here's a general terminology, T with a vector on top. I had that for the pressure, I had that formula for the shear. So it's the force by the area, and it's S goes to 0, so it's a point. So if I'm looking at a point, then the force can have different direction, the resultant. But it could be a result of the normal force, which is the pressure, and it could be a result of the shear. Shear can have 2 components. So X,
Professor?
yes.
What is vector T, where it's a limited?
It is a generic vector, which could be pressure, could be shear, could be both. Again, in mechanics, people use that. I'm not going to bother you too much, but this is I assume that you did statics, and then did the professor in materials or statics use something like that?
It was a little bit back, so I don't know, but I'm sure they did, yes.
Something similar. I'm just trying to pull equations from your previous studies. Maybe I'm not successful. I'm trying. Anyway, so I'm just trying to say that, okay, you have a surface something. Okay, so say this is the fish, okay? And this is the back of the fish, and I'm picking up an area on the back of the fish. And I want to find out what are the forces acting on the poor guy. And there's going to be the pressure, which is acting normal. And because he's swimming fast, there is shear on it, okay? And then
Yes.
what is the total resultant is going to be something F, something like that. So, and then we have his limit, we have all this fancy description just to show that this is a point, and then the next point, those things could be slightly different. Okay, that's all. That's nothing, no rocket science. And then I'm
Okay.
going back to your material sciences, and I'm not going to bother you too much with that. But you said, what is T? They use tau instead. So some people use X, Y, Z, like here. And then some people use 1, 2, 3, and then they call it tau RJ. And these are some different, okay? So that's probably the best way to explain it with the little box. So what are the forces in a box? Let's think that this is just a solid box, okay? Just a solid box. So we're talking mechanics now. So what kind of forces can I apply? Let's say on the upper surface, I can have, and then here's the coordinate system. And usually we're going to say that the force direction is going to be, let's say, Z, okay? So then the direction of the plate, the normal to the surface is also Z because the normal is Z. Therefore, the pressure we're going to call tau ZZ. Have you done it in other, you must have done it in other courses, the naming those forces. Okay, so each of these sides of the cube will see 3 different forces, okay? One of them is the pressure. One of them is the shear to this direction, which is the X. Therefore, we're going to call it tau to the X direction, acting on the surface, which normal is to the Z direction. And this one is acting to the Y direction, and therefore it's going to be Y, but Z is the normal of the surface direction, okay? And the same way we describe the story on these other sides and so forth. Am I inventing anything new or? Okay, so hopefully I'm not boring you. Let me just throw a little bomb here and then I let you go. Okay, let me scare you a little bit. Okay, so if you guys took materials, then the professor told you that actually this tau guy, which I'm trying to show very simplistic here. So what I used 1, 2, 3 per side, okay? So this is going to be to the X direction, Y direction, Z direction. They actually show you this equation. So this one, in general, it's exactly what I discussed earlier, but this one will have the pressure outside and we'll have compression. So let me not scare, I'm not going to do that, but I'm just trying to show you that, hey, I can make life much more complicated. So for example, there's another box next to this one, and I'm going to compress the other box. Because I'm compressing the other box, there is going to be an additional shear on that surface due to the compression of the other box. This one, this fancy term represents that. And of course, the delta function is 1 when the XX, YY, but the XY is 0, okay? So if I talk to those that have seen that before, I'm lucky. If I'm talking to those that never heard about that, no harm done, because I'm going to use it just once to show you something and that's it. So this is not crucial, but it would be nice if you remember this story. I think we're running towards the end of the class and I don't want to scare you too much. And again, next week, we're going to focus on developing the equations. And I will do that initially in integral form. Let me stop share. I will do integral form, and then we'll do examples in an integral form. And it's going to be very easy. You're going to like that. You say, hey, I understand that. Then I'm going to throw at you the differential form, which is going to be more mathematical. And you may not